half-life is defined as the time it takes for half of your sample to react. Often we think about half-life in reference to radioactive decay, and if I had a 100-gram sample of a radioactive substance, half-life is the time it takes for that 100-gram sample to decay down to a 50-gram sample. But we can also think about half-life in reference to any reaction. It's the time it takes for half of the original sample to react. In this case, I've got initially, here we go, 0.1 moles of N2O5 per liter. It looks like the unit is moles per liter. My initial sample is 0.1 moles per liter. And if I look at the graph, I just want to find the amount of time it takes for that 0.1 moles per liter sample to go down to 0.05. So I find 0.05 moles per liter, and I'm looking at the time. So it looks to me like it takes a total of 100 seconds. Well, the thing about half-life is that after every 100 seconds, the concentration continues to decrease by half. So after another 100 seconds, here's my first 100. Now when I'm at 200, oh, look at this. My 0.05 moles per liter is down by half again, 0.025. After another 100 seconds, my 0.025 is down again, maybe about like 0.0125, and so on, until eventually we have a sample size that is too small to measure. Here's a great graph showing half-life. Now, what they're not showing is that if you were to change the axes, and instead of just graphing concentration versus time, if we change this to a natural log of the concentration versus time graph, we would get a linear fit, which is why half-life is a first-order reaction. I would get a linear fit if I changed the axes to natural log of the concentration versus time. It's also a way of identifying a first-order reaction if you recognize a constant half-life. So maybe they gave me a graph like this and said, hey, what's the order? And you're like, oh my gosh, I don't know, it's not linear. I'm looking for the linear fit. Look for half-life. This is a real common type of question that they'll throw on an AP exam, where they may not give you the linear graph, but I bet it might be first order. If I look at the initial concentration and figure out the time it takes for the initial to go down by half, see if that time is consistent. That, like in this case, after every 100 seconds, the concentration continues to decrease by half. And if you find that there would be a consistent half-life, bingo, you've got a first-order reaction. Now, if I wanted to calculate the half-life, if I wasn't given a graph, we could use the first-order integrated equation, which is in my packet. It's the second one listed in the kinetics section. It's listed in your packet like this. Natural log of A, which is just whatever reactant I'm studying, at time t, minus natural log of A initial equals opposite KT. So we could just use the first order integrated equation. Let's see here. I would probably have the constant. Maybe they would give me the constant. Maybe I would have a graph, or I could figure out the constant. Then this just becomes natural log of the initial concentration, which, I don't know, like in this case, maybe it is something like 0.1 molar, or moles per liter. Well, often then, if I'm solving for half-life, I want to know time. How much time does it take for that initial concentration to go down by half? And sometimes kids will get a little confused because they'll say, well, gosh, they're not giving me enough information. They give me the constant, they give me the initial, but I don't know the concentration at time t. Oh, yes, you do. If they're referencing half-life, It's the time it takes for the initial to go down by half. So whatever the initial is, just bring it down by half and solve for the time. Which again, they'd probably either give you the value of k, or maybe I would have had a graph and I could find the slope of that linear fit. Option 1. Here's option 1 in solving for half-life. However, there is an option 2. In the packet, there's one last equation in this kinetics section. It looks like this. 0.693 over k. I almost feel like it's a bit of a cop-out because it's super easy. But guess what T1/2 stands for? Half-life. And so if you know the constant, which again, you'd probably either have a linear graph, I could find the slope, or sometimes you're just given the value of k. To find the half-life, you just plug it in. 0.693 divided by your constant. It comes from this integrated equation with the natural log, that if you simplify this, you would get 0.693 over your constant. But the constant is going to be dependent on the temperature and the particular reaction that we're running. So that would change. I need to know my constant. But then it's just 0.693 over k. So I guess in this case, take your pick. Whichever one you prefer will get you to the same half-life, and they're both 100% acceptable. Most important thing is to recognize that half-life is a first-order reaction.